Hi, this section is about exponential functions, their characteristics, and their graphs. So first let's talk about what a rational number is. So remember, a rational number is a fraction, and a rational number could be an exponent. So just to review some of the rules that we know from algebra, 4 to the 1/2 is the same as square root of 4. So that's why 4 to the 1/2 equals 2. 4 to the negative 1/2, well, that would be 1 over the square root of 4. So that's why 4 to the negative 1/2 is equal to a half, because the square root of 4 is 2. Negative exponents flip the base, meaning you take the reciprocal of the base, so the 4 goes into the denominator, and then the exponent turns positive, and a 1/2 means the same thing as a square root. And then if you're multiplying exponential expressions, remember, as long as the base is the same, and the base could be a variable or a number, but if they are the same, you're just adding your exponents. So 2/5 plus 1/3 is where we get the 11/5 from. 11/15. And if you have a power raised to a power, like in this case, you multiply your exponents. So 4 times 3/2 gives you 6 as an exponent, so x to the 6th. So just to remind you about radicals and rational exponents, if you have an exponential expression raised to a rational exponent like x to the m over n, that can get rewritten as a radical as the nth root of x to the mth power. So the denominator of the exponent becomes the root of the radical, and the rest of it goes on the inside, and that's called the radicand. Remember that the expression that's raised to that power is called the base. So here my base is 4, but in this example, your base is x. Okay, so an exponential function is a function where the exponent is a variable. So instead of having a number in the exponent, you have a variable, such as something like this, y equals b to the x, where x can be any real number, meaning it could be positive or negative, a fraction, a decimal, it could really be any real number. But your base must be positive, and the base must not equal 1, because 1 to a power, remember, 1 raised to any exponent is just equal to 1, so that would be a constant. So that would not be an exponential function. So we call b the base. The x-axis will always be a horizontal asymptote to these types of functions. And the x-axis can be stated as the line y equal to 0. So b must be positive, because when a negative number is raised to a rational exponent, then you end up with complex numbers, like in this case, negative 9 to the 1/2 is equal to 3i. So anything that we're trying to graph, like an exponential function in this case, must result in real numbers, not imaginary numbers. So you don't graph imaginary numbers on an xy plane. And as I mentioned before, the reason why b can't be equal to 1 is because it would be a constant, and that's considered a linear function, a horizontal line. All right, so for example, 2 to the x is an exponential function, but negative 2 in parentheses to the x is not, because here your base is negative, and we know that doesn't satisfy the condition that is stated above. In this case, although it looks similar, negative 2 to the x, where the negative is before the 2, but it's not surrounded by parentheses for the x. In this case, the base is 2, and you're just taking the opposite sign of the result. So the base is positive, and a number greater than 1 in this case. So the square root of 2 to the x power is also exponential, because root 2 is positive, and it's the base. And 2 to the negative x is also a rational exponent because 2 to the negative x can be rewritten as 1 over 2 to the x power. So your base is positive. Because remember, negative exponents mean you take the reciprocal of the base and the exponent changes to positive. All right, so we're going to just practice evaluating some of these. Suppose I have y equal to 2 to the x, and we want to simplify or evaluate it for x equal to 0, 1, 2, and 3. So 2, or any base to the 0 power, is 1. 2 to the first power is 2. 2 to the second power is 4. And 2 to the third power means you multiply 2 3 times, and you get 8. So the exponent gets replaced by these numbers to come up with the values below. So we can do that again with a different rational function, 3 to the x. This time I've picked negative values of x. So 3 to the negative 3, that's the same as 1 over 3 to the positive 3. So that's equal to 1 over 27. Then 3 to the negative 2, that's the same as 1 over 3 squared, so that's 1/9. And 3 to the negative 1 is equal to 1/3. So your x values can be positive or negative or 0. So here's an example of a rational function where your x values are, I have 0 as well as a few fractions. So 9 to the negative 1/2, that's the same as 1 over 9 to the 1/2. But 1/2 as an exponent means that that's the same as a square root. Square root of 9 is 3. So 9 to the negative 1/2 is equal to 1/3. Again, anything to the 0 power is 1. So 9 to the 0 is 1. 9 to the 1/2, this time we don't have to take the reciprocal because the 1/2 is positive. So that's just equal to the square root of 9, which is 3. And then we have 9 to the 3/2. So remember that denominator is your root, and when it's a 2, it's a square root. So it's the square root of 9 to the 3rd power. Square root of 9 is 3, but then you still have to cube it. So that's equal to 27. All right, so if your exponents are numbers that aren't easy to manage, like these, negative 0.2, root 3, and 3.5, we need to use a calculator to help us evaluate this because these will be irrational numbers. So in your calculator, you should have a key that allows you to raise something to a power, and your power are going to be these 3 numbers. So 5 to the negative 0.2 gives you this approximate answer. This curly equal sign means approximately equal to. So it's 0.725 or 725 thousandths because you were told to round to the thousands place. 5 to the square root of 2 is approximately equal to 9.739. And 5 to the 3.05 is 135.475. Remember your rounding rules. If the digit that's next to the position you're rounding is 5 or more, the digit that you're rounding to, in this case the thousandths place, the 3rd position to the right of the decimal will go up. If the digit next to it is less than 5, like 0, 1, 2, 3, or 4, the thousandths place stays the same. All right, so characteristics of these exponential functions when you graph them, this is really helpful. The domain, or the x values, will always be all real numbers, and the range will always be positive. So any base raised to any power will give you a range that is positive. The x-axis is an asymptote, and that can be stated as y equal to 0. X increases from left to right as long as the base is greater than 1. and it decreases from left to right as long as your base is between 0 and 1. So a proper fraction or a decimal between 0 and 1 could, as long as the base falls within that. The graph of b to the x, no matter what b is, as long as b is greater than 0, it will have a y-intercept at 0, 1. So that'll be where it crosses the y-axis. All right, so here's a graph of an example of an exponential function, y equals 2 to the x. So this falls in this category. B is greater than 0. So in order to get a few points, I picked some values for x, some negative at 0 and at 1. And if you plug that into your x values here, you'll get the y values here. So 2 to the negative 2 is a fourth, 2 to the negative 1 is a half, 2 to the 0 is 1, 2 to the first power is 2, 2 to the second power is 4. So all of those points were graphed here. And you can see that as your values become more negative, the y values get smaller. So negative 1 is a half, but at negative 2 it's a quarter. At negative 3 it'll be an eighth. So they'll just keep getting smaller as you go further left. So it gets close to the x-axis, but it'll never quite touch it. So that's why the x-axis is an asymptote. And the bigger your x's get, the bigger your y's will get. So when x is 3, this will be 8. When x is 4, this will be 16. So the y's grow pretty quickly. That's why you may have heard the expression exponential growth. So this is an example of what the graph of of something that's growing exponentially would look like. So this grows very quickly in this direction, so it goes towards infinity. So just to recap some of the characteristics that I mentioned above here on the right, the domain is all real numbers. The range is from 0 to infinity, not including 0. The horizontal asymptote is the x-axis, which we stated as y equal to 0. It increases from left to right over all real numbers. And our y-intercept is at 0, 1, which is also indicated here in that bright blue color. All right, so here's an example of a graph where your base is between 0 and 1. My base here is a half, which means it could also get rewritten like this as 2 to the negative x, because remember, negative exponents mean that you flip the base. So it's two different ways of writing the same function. Again, if I pick these values of x and I plug in here, you'll get the values on the right for y. So 1/2 to the negative 2 is 4, 1/2 to the negative 1 is 2, 1/2 to the 0 is 1, 1/2 to the first is a half, 1/2 to the second is a quarter. So my y values are in reverse from what we saw up here. So just notice the y values are actually going in the opposite order. And when you graph them, you'll get the graph that you see here in green. So it looks similar in shape, but it's going in the other direction. So again, to just review the characteristics, domain is all real numbers, range is from 0 to infinity, horizontal asymptote is the line y equal to 0. It decreases over all real numbers, so from left to right, this graph should always be going down. And again, it has a y-intercept at 0, 1, which is the point here indicated in blue. Okay, so all exponential functions where b is greater than 1, the base is greater than 1, will look like the first one we did above, 2 to the x, meaning going upward from left to right. And all exponential functions where your base is between 0 and 1 will look similar to, look similar to y equals 1/2 to the x. So in other words, going downward from left to right. So they don't have to be 2.5, 2 as a base or 1/2 as a base. You could graph 3 to the x, 5 to the x, 20 to the x, but anything greater than 1 will look more like this one. And here as well, you could graph 1/3 to the x, 1/4 to the x, 3/5 to the x. As long as it's between 0 and 1, it will look more like this graph. Okay, so we want to describe the shift of y equals 4 to the x plus 2 from the original function y equals 4 to the x. Remember, 4 to the x will look more like this graph, increasing from left to right. So this one has, we want to state the shift, the asymptote, and the y-intercept. So this one has a horizontal shift 2 units to the left, because remember, the 2 is impacting the x directly. It is not impacting the entire function of 4 to the x. So it has no vertical shift, just a horizontal shift 2 units to the left. The horizontal asymptote stays the same as y equal to 0. And the y-intercept, well, that's when x is equal to 0. And if you plug in 0 in 4 equal to x plus 2, right in here, you plug in 0, you'll have 4 squared, so your y-intercept is at 0, 16. So similar example, we want to describe the shift of y equals 3 to the x, and then minus 2. So the minus 2 is big. It's not in the exponent. From the function, the original function of y equals 3 to the x, we're going to state the horizontal asymptote and the y-intercept. So this one is a vertical shift, and it's going downward. So it shifts this original function, which looks a lot like the one we graphed before of 2 to the x, and it shifts it down 2 whole units. And because it shifts the whole function down, that means your horizontal asymptote shifts 2 units. So your horizontal asymptote will be y equals -2. And your y-intercept, well, that's when x is 0. Plug that in here. 3 to the 0 is 1. 1 minus 2 is -1. So we have a y-intercept at 0, -1. So your shifts could impact some of the characteristics that were discussed above. All right, so that's your lesson on exponential functions and their graphs. Give the homework a try. Good luck.